screen. So can you see the screen? Okay. Okay. So this is about connectivity, edge connectivity. So there is a problem saying that if you want to start from one place and come back to the same place by covering all these bridges exactly one time, is that possible? Anyone tried? Anyone got a tour or a walk where it is covered exactly, it covered all the bridges one and only one time and come back to the original position? Was it possible? So if you see, if you are starting like this, okay, go like this and go like this and go like this. If you go like this, then if you want to cover these bridges, then you have to cross one of the bridges. So repetition, that is not allowed. Or you go like this, 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 you go like this. Okay, you go like this. Okay, but I want to reach to this point. If I want to reach to this point, again I have to cross the bridge one more time. That means edge repetition is there. So whatever the point you stay, you choose. Okay, whether you are starting from this land or this land or this land or this land. There are four lands: land A, land B, land C, land D, and these four lands are connected by seven bridges. 1, 2, 3, 4, 5, 6, 7. Okay, so these four lands are connected by 7 bridges, and you have to start from any one land and reach to the same land by covering all the bridges one and only one time. That is the problem. Do you understand what the question is all about? Hello?
Yes, sir.
Right. So that can be converted into a graph theory problem. Like you can consider each land as a vertex. Okay, and these are the bridges connecting those vertices. Bridges are the edges which are connecting those vertices. So you can see like this. Okay, so land 1, land 2, land 3, land 4, land 1, land 2, land 3, land 4. Okay, or you can draw the same graph like this also: land 1, land 2, land 3, land 4, and there are 7 bridges: 1, 2, 3, 4, 5, 6, 7. Okay, now the question is, can you start from one node and come back to the same node by covering all the edges? Okay, so that is the problem. Okay, so if you see the possible ways, okay, so whatever the way you choose, okay, if you want to come back to the original position, you need to cross the edge more than one times, not exactly. You need to visit the edge exactly more, at least 2 times, then only will be able to come back to this original position. Okay, so so now the question is, okay, when such thing happens, okay, when which graphs will have that property? Okay, so that is given by Euler. Okay, okay. So first see the definition. Okay, what do you mean by Eulerian trial? Eulerian trial, which contains all edges of the graph. Okay, so you know trial is nothing but a walk. Okay, trial is nothing but a walk in which all the edges are distinct. Okay, the edges in the trial need not be all the edges of the graph. Okay, you may just my trial may be from A to C, C to D, D to E. This is one trial. Okay, this trial containing only 3 edges. Okay, another trial can be A to D, D to B, B to C, and this is containing again 3 edges. Okay, so like that you can have several trials containing distinct edges of the graph. But if your trial containing all the edges of the graph, then that trial is said to be Eulerian trial. And you know the difference between a trial and a walk, right? Okay, in a walk edges may repeat, vertices may repeat, but in a trial edges cannot be repeated. Am I right? So each edge occurs one and only one time, and like that, if all the edges are present in that trial, if all the edges are present in that trial, then that is said to be Eulerian trial. Okay, and if that Eulerian trial is closed trial, that means all the edges are distinct and initial vertex is equal to the terminal vertex. Then that is called closed trial. Okay, so the graph is said to be Eulerian if the graph is containing a Eulerian trial. Okay, so you may visit the vertex more than one time. You can visit the vertex more than one time. Vertices may repeat in a trial, but edges cannot be repeated in a trial. Okay, so so if you are able to draw like that, then that is said to be a Eulerian trial. Okay, then that graph is said to be Eulerian. Okay, so if graph contains a closed trial, okay, if a graph contains a closed Eulerian trial, then that is said to be Eulerian graph. That is said to be a Eulerian graph. Now, can you tell me, is this Eulerian or not? I will draw this graph in this one note. Tell me the uh, so is there any Eulerian path or Eulerian closed Eulerian trial? Path is different from trial. I am talking about trial. Okay. So this is A, B, C, D. So if I start with A, so can we cover all the edges by visiting exactly one and only one time? Is it possible?
Yes, sir.
Can you tell me A to what vertex I have to go?
Sir, from C we can do it, no, sir.
Okay, you tell me.
C, A, B.
Wait. So C to
No, sir. 1 second, sir.
you take the time.
C, D, A, B, E, C, A.
C D
D,
A
B,
B.
E, C. Oh, it misses B, sir. So from B we can start, no, sir.
You
B,
just
C.
take, all of you take your time. Just put it on the paper and tell me whether you are able to get it or not.
Sir, it can be B, C, D,
E, C, A.
A. Yeah, B, C, A.
Tell me. Tell me.
B, C, D, A, B, E,
B
C, A.
C D
B, A,
A
B,
B
E,
B
C,
C.
A.
Okay. So let me give B to C and C to D and D to A, A to B and B to E and E to C, okay, and C to C. But so what is this called? What is this called? This is a trial, right? What kind of trial it is?
Eulerian trial, sir.
Eulerian trial, right? So Eulerian trial is existing. Is Eulerian? Is it Eulerian? Is the graph Eulerian? I'm asking. So there is G has any Eulerian trial. I agree. I'm asking. G has Eulerian tour. What do you mean by tour? Tour means what? You go somewhere and come back, right? And you go somewhere and come back by visiting each edge one and only one time. So when you start with B, can you come to B by covering all the edges exactly one time? So here initial vertex is different from terminal vertex, right? If I want to come back to B, from A, so I covered all the edges, but if I want to come back to B, again you have to use this edge one more time. Can you see that? Did you realize this point? All the edges are covered, but you are not able to come to the original point, right? Suppose if the graph is simple like this. What about this? You start with any vertex and you can come back to the original vertex by covering all the edges. Okay, so G has a closed Eulerian trial or closed Eulerian, or G has a Eulerian tool. Therefore, G is Eulerian. Okay, is it having that? Do you find such a tour here? Starting from one vertex and coming back to the same edge just by visiting one and only one time each edge. Is it possible? Check once. You explore all possible ways. Okay. So why? Because you are not able to find out, right? And here you are able to find out. Even my graph can be like this also. You see, my graph can be like this also. You see, if it is okay. Okay, but if it is like this, will you have the tool? Start from, let us say A to B, let us say B to C, C to D, and D to A. You can come back, but that is not a tour because Eulerian tour, because you left out this edge. If I want to go cover this edge also, then I have to take the edge repeatedly. Then only I can come back. Okay. So if that is the case, such a tour does not exist. Okay. So why? Because whenever there is an odd degree vertex, Eulerian tour does not exist. Okay. So here each vertex is of even degree, therefore Eulerian tour is existing. Okay. So if in this case, what are the odd degree vertices? You see here 1, 2, 3. There is an odd degree vertex. 1, 2, 3. There is an odd degree vertex. 1, 2, 3. There is an odd degree vertex. This is 1, 2, 3, 4. Okay, these two are odd degree vertices. That's why it is not having Eulerian tour. Okay, and here also, where is this? In the Königsberg bridge problem also. Here in this problem also you see there is an odd degree vertex. See, and there is 1, 2, 3, 1, 2, 3. This is an odd degree vertex. 1, 2, 3. Okay, this is an odd degree vertex. 1, 2, 3, 4, 5. So in Eulerian graph can be multi-graph also. It is not necessary that it should be a simple graph. Okay, you can see multiple edges between two nodes. Okay, so that is one point to note. Okay, so far in trees and all, we discussed about simple graphs only, because every tree is a simple graph. But Eulerian graph not necessarily simple graph. So this is a multi-graph. This is also a multi-graph. You can discuss tours. You can discuss tours even in multi-graphs also, not necessarily in simple graph. Okay. So what is the necessary and sufficient condition for existence of Eulerian? Okay. A connected graph G is Eulerian if and only if every vertex is of even degree. A connected graph G is Eulerian if and only if every vertex is has even degree. Because this is not having because some of the vertices are not of even degree. Therefore, there is no. This graph cannot be called as a Eulerian because there is no Eulerian tour. Okay, but Eulerian trial is existing. Why? Because there are some. There is an odd degree vertices. If there are exactly two, then Eulerian path exists. Eulerian trial exists. Okay. So a connected graph G has Eulerian trial if and only if G has only two nodes of odd degree. Because G is having only two nodes of odd degree, you are able to find out such Eulerian trial. Okay. And please remember the difference between trial and a path. In a path, vertices are also distinct. You cannot visit the same vertex in a path except end if it is a cycle. But in a trial, vertices may repeat. Only thing, edges should not repeat. Okay. So always remember that. Okay. A walk may contain repeated vertices and repeated edges. And this walk becomes a trial if the edges are not repeating. And this trial becomes a path. Okay, if this trial becomes path if vertices are also not repeating. And special case of trial is closed trial. And special case of path is not special case. An extension to path is closed path. That closed path we are calling it as cycle. Closed path we are calling it as cycle. Okay. So in trial, vertices may repeat. Remember that. Okay. But here vertices and hence edges will not be repeated. Okay. So that's the difference. So if the graph is containing exactly two odd degree vertices, then that will definitely have a Eulerian trial. If the graph is not containing any odd degree vertex, then only it will be Eulerian. Okay. So a graph will be Eulerian. That means a graph will have a Eulerian tour. Okay. Only when each degree is of even degree. Each vertex is of even degree vertex. Okay. That is what these two theorems are telling. Even if you see one odd degree vertex, it cannot be Eulerian. And if there are exactly only two odd degree vertices, then that will definitely have a Eulerian trial. Okay. So this is about how you are traversing along this. And now this is about path. See, Hamiltonian graph is talking about the paths and cycles. Okay. And Eulerian graphs are talking about edges, trials and closed trials. Okay. Eulerian Hamiltonian is talking about paths and closed paths. So what do you mean by Hamiltonian path? Okay, path is said to be Hamiltonian path. Okay, if that containing all the vertices. Okay, so if the path is containing all the vertices of the graph, then that is said to be a Hamiltonian path. Okay, so in that some of the edges may be omitted. Some of the edges may be omitted. We don't care whether we are covering all the edges or not, but we only have to care whether we are covering all the vertices and exactly one times. And why I am telling exactly one time? Because I am referring to path. Path means vertex cannot be repeated, and Hamiltonian path means all the vertices must be covered. So Hamiltonian plus path. Okay. So all the vertices must be visited one and exactly one time. Such a path is said to be Hamiltonian path. Okay. So in this case. This is is this Hamiltonian? You start with vertex A, visit B, visit C, visit D. Okay, what is one path? You can omit this one. Okay, so this is what is the path? So if you are calling this as E1, E2, E3, E4, my Hamiltonian path could be A, E1, B, E2, C, E3, D. Okay, so all the vertices are covered and all the vertices are visited exactly one and only one time. So this is one Hamiltonian path. Do you agree? Okay, we may leave some of the edges, doesn't matter. Okay, but we have to visit all the vertices one and only one time. Okay, and what do you mean by Hamiltonian? If the graph is containing a Hamiltonian cycle, what do you mean by cycle? A closed path. Okay, so what is that? So this is called Hamiltonian path. Hamiltonian path. So what is Hamiltonian cycle? A, E1, B, E2, C, E3, D, E4 and A. Now you see, except this is a cycle because initial vertex is equal to terminal vertex and all the vertices are distinct. All the remaining vertices are visited one and only one time. Therefore, it is a Hamiltonian cycle. And any graph which containing Hamiltonian cycle is said to be Hamiltonian. 1 second. Okay. So similarly, where is my pen? Similarly, if I have a graph like this, okay, if I have a graph like this, okay. So what is this Hamiltonian? If I say A, B, C, D, okay, you can start with one vertex Okay, Hamiltonian means it should have a Hamiltonian cycle. Okay, Hamiltonian cycle is a closed path consisting of all the vertices. Okay, so A, B. So I visited A, I visited B, I visited C, and I visited D also. If I go like this, okay. Is there any other Hamiltonian? Or I can go like this from A to C, C to B, C to B, and B to D. You can go like this also, right? So A to C, C to B, and B to D. This is also and D to A, D to A. So that I listed all the vertices A, C, D, uh, B, D, A. So there is a Hamiltonian cycle. Therefore, this is Hamiltonian. Therefore, this is Hamiltonian. Okay. So, so if this closed trail is existing in a graph, then that is said to be Eulerian. And if this closed cycle, okay, closed what kind of trial? Eulerian trial. Okay, so I will write it as a special case. Trial need not contain all the edges. Trial need not contain all the edges. Therefore, a special case of this is closed Eulerian trial, which contains all the edges. And special case of this is uh, Hamiltonian cycle. Hamiltonian cycle. Okay, so what is the thing you have to remember? Eulerian trial will have contains all edges, and Hamiltonian cycle will have contains all vertices. Okay, so here you can visit the vertex more than one time, and here you can omit some of the edges in the graph in the tool. Okay, so can be omitted. Okay, so can may visit the vertex more than once. Okay, so in this, okay, may omit some of edges. Okay, you can omit some of the edges. Okay, so any graph containing Hamiltonian cycle is said to be Hamiltonian. Any graph containing Eulerian closed Eulerian trial is said to be Eulerian. Okay, so now if you see this one, okay, is this is called I don't know, dodecahedron. So is this Hamiltonian? Okay, so he is able to show it as a Hamiltonian. See the tool. You start with one vertex. You try to cover all the vertices by visiting exactly one and only one time. So you go from this vertex, cover 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 this, visit 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 this. Okay, so we visited all the cities, or we visited every node exactly one and one time, starting from this node, and we came back. Okay, so there is a Hamiltonian cycle present in this graph. Therefore, this graph is said to be Hamiltonian. In this, we neglected some of the edges. Can you see that? We did not visit this edge. Do you see? Is it clear? Is this Hamiltonian? Hamiltonian?
Yes, sir. All edges are included.
Tell me, Hamiltonian means it should have a Hamiltonian cycle. Okay, so let us say U1, U2, U3, U4, U5. Tell me, you start with some vertex and come back to the same vertex by visiting each vertex one and only one time. Tell me which one that is. You want to start with the U3?
Sir, wherever we start, sir, we'll be crossing U2 twice.
Yeah. So you cannot come back to the original vertex by visiting exactly one and only one time, right? So if I'm starting, let us say U3, covering like this. So visited one time, okay, and visited one time. But if I want to visit, okay, you have to go in this edge only. Visited one time. But I have to come back to this, no, because I want a cycle. If I want to call this as a Hamiltonian, there should exist a Hamiltonian cycle. Okay, cycle in which vertices are not repeated, right? So if I'm coming back to this, that means vertex is repeated. That means cycle is not existing. Cycle is not at all existing. Closed walk existing. U1 to U2, U2 to U3. Closed walk existing, but cycle, Hamiltonian cycle does not exist. Okay, so that is the case. Whatever the vertex you start with, therefore this cannot be Hamiltonian. Am I right? Do you agree?
Yes, sir.
Right. So there are some necessary conditions for it to test whether a graph is Hamiltonian or not. So before that, let us draw this graph also. Tell me whether this is Eulerian or Hamiltonian. This is the graph.
Eulerian, sir.
Because the way I am drawing, you can see that this is a Eulerian, right? So 1, 2, 3, 4, 5, 6, 7, 8. Okay, I visited all the edges. I covered all the edges, and I came back to the original vertex. Therefore, I got a closed Eulerian trial. Therefore, this is Eulerian. So in that covering, I may visit the vertex more than one time. You see, already visited one time. Now, if I want to come to this, I am visiting this vertex second time. Doesn't matter. I want to visit the edge only one and only one time, so that is possible. So this is Eulerian. I agree. And if it is Eulerian, you must observe that there should not be any odd degree vertex. Is there any odd degree vertex? What is its degree? 2. What is its degree? 2. What is its degree?
4.
4. Degree 2. 2. 2. 2. That's why it is Eulerian. If you see any odd degree vertex, immediately you can say that, sir, this cannot be Eulerian. Because there is an odd degree. When there is an odd degree, you can never get a closed Eulerian trial. Is it fine? Now you tell me, is it Hamiltonian also?
Sir,
Hamiltonian.
wherever you start, the one in the middle gets repeated, sir. Yeah, F vertex gets repeated.
So wherever you start with, if I want to come back to the same vertex, then I have to visit the vertex F. No, I have to visit the node F more than one time, right? Or if I am starting with F itself, F, C, D, E, and G, A. Okay, and that means vertex is repeating. Okay, not for initial and terminal, in between also. Okay, so it is not containing any Hamiltonian cycle, therefore it is Eulerian but not Hamiltonian. Okay, so this is Eulerian but not Hamiltonian, and whereas your previous graph Hamiltonian but not Eulerian. Do you agree? Can you tell me why it cannot be Eulerian?
It is having odd degree vertices.
There are some odd degree vertices. That's why you will have to omit some of the edges. You cannot cover all the edges. Is that clear? Okay. What are the necessary conditions for Hamiltonian graph? Okay, there are some theorems like this. If G is simple graph, okay, so for Hamiltonians we are talking about simple graphs now. The theorems are on simple graphs. If G is a simple graph with n vertices, where the number of vertices are at least 3, such that the degree of every vertex in G is at least n by 2, then G has Hamiltonian circuit. Okay, if then you see, you observe this statement, this is if part. If this condition is satisfied, then it is going to be Hamiltonian. What is that condition? Every degree should have at least n by 2 degree. Okay, so it is in the form you studied logic, right? If P, what is P? Some condition. If condition is satisfied, then G is Hamiltonian. That is what the theorem says. Okay, so tell me, is this condition called a necessary condition or sufficient condition for a G to be Hamiltonian? If P, then Q in logic. P implies Q. Do you remember? For Q, is this necessary or sufficient? If you get 90 mass, then you will pass. Then you pass, otherwise you say. Okay, so to pass the exam, getting 90, is this necessary or sufficient?
Necessary.
Sufficient, sir.
Necessary. Yeah.
No, sir. Sufficient, sir.
Sufficient, right? So if this condition is satisfied, you will pass. If this condition is not satisfied, will you say that you will not pass? May or may not, right? Because that is inverse. I said only what is the equivalent statement to P implies Q? P implies Q is equivalent to negation Q implies negation Q. Do you remember? Only contrapositive is equivalent. Okay, converse need not be equivalent. What is converse? Q implies P. These two need not be equivalent. You remember, converse need not be equivalent. Inverse also need not be equivalent. This is not the case. Okay, so this is only a sufficient condition. If each degree has at least, if the degree of each vertex is at least n by 2, then it is going to be Hamiltonian. That doesn't mean that in a Hamiltonian every vertex is having at least n by 2 degree. Do you understand? For example, if you take this one, 1, 2, 3, 4, we observe that it is a Hamiltonian because it is a Hamiltonian cycle. And what is the degree of each vertex? 2, which is half of the number of vertices. So because it's satisfied, you can see it is a Hamiltonian. Whereas here you see in this graph there are several vertices. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It is more than 15 to 20 vertices. And what is the degree of this vertex? 1, 2, 3. And is it greater than 15 by 2? Is it greater than 2 or is it greater than 7? This condition is not satisfied, no. This condition is not satisfied, but still it is Hamiltonian. That's why I am telling this is only a sufficient condition. This is only a sufficient condition, but not a necessary condition. Similarly, there is one more sufficient condition. Okay, if this condition is satisfied, then G is Hamiltonian. G has a Hamiltonian circuit, or G is Hamiltonian. What is that condition? Okay, if G in a simple graph with at least 3 vertices, okay, if the degree of U plus degree of E is greater than or equal to N for every pair of non-adjacent vertices, you take any 2 non-adjacent vertices, their sum must be greater than the total number of vertices. If that is the case for every pair of non-adjacent vertices, then definitely it is going to be Hamiltonian. Hamiltonian need not have this property, but if this property is satisfied, it is going to be Hamiltonian. So these two are only sufficient conditions for a graph to be called as a sufficient Hamiltonian graph. If this condition is satisfied, there will be Hamiltonian cycle. If this condition is satisfied, in that case also Hamiltonian cycle will exist. Is that okay? I think you have another class, right? You have second hour, no?